Welcome to part 5 of our solution. So in this video we now want to use the power and speed of our NumPy code to optimize our selection strategies. And first of all, we are working and optimizing the strategy where we split our total number of applicants into a test group and select group, and then we have the best prints in our test group as reference prints. So we use here nBest equals 1. And first of all, we want to maximize the probability of getting Prince Charming. And we already know from the solution with Python standard library code that there is an optimal test group size where we can maximize the probability. And first of all, here we are starting with 100 applicants. And we are calling our princess function 100 times. So we are using all possible test group sizes, so from 1 till 100 including. And our princess function calculates 100 times the probability of getting Prince Charming, and we are using 10,000 simulations. And then we are storing our 100 results in the results lists results 10,000 simulations. And then we want to plot our results on the y-axis, and on the x-axis is the test group size. So we did this already in the Python standard library solution, so this is nothing new. And now first of all, let's calculate the probability of getting Prince Charming for each possible test group size here and store it in the list the results 10,000 simulations. So even if now our NumPy code is now faster, it takes a while here. Now we are finished. And we import matplotlib, and we also want to use the interactive graph. So we have here matplotlib notebook. And now on the x-axis we are plotting actually the test group sizes, so from 1 to 100. And on the y-axis we have our probabilities of getting Prince Charming. And let's run here the cell. So here we are getting an interactive graph. And we have here on the x-axis the test group size, and on the y-axis the probability of selecting Prince Charming. And we can see that here somewhere between a test group size of 30 to 40 there's a maximum here. And we can also zoom in here with our interactive graph. So here there's a maximum at the test group size 35, and the probability is here 36.6%. Alright, so now let's go back here. And let's also close here the interactive mode. And now we want to define more precisely where the maximum is actually located. And therefore, in order to get a more precise result, we have to scale our case to 1,000 applicants. Because with 100 applicants, we could only increase the relative test group size from, let's say, 35% to 36%. So the steps are quite large. However, now with 1,000 applicants, we can reduce the steps, and calculating the probability of getting Prince Charming for a relative test group size of 35.0% and then 35.1%. So we have here quite small steps, and therefore we can increase the precision of our analysis here. Alright, so now we have 1,000 applicants, and we are calculating for each test group size between 350 and 400, so the maximum should be somewhere here between 35% and 40% of the total amount of applicants. And we are calculating the probability of getting Prince Charming, and we are using 50,000 simulations. So this is actually quite a lot, and we should be able to further reduce the random noise. So we are calling here our princess function 50 or 49 times, and we are storing the results in the list the results 50,000 simulations, and then we again plot our results here in an interactive graph. So let's do this, and I would assume that here the calculation takes a while. So we have 1,000 applicants and 50,000 simulations, so that's quite a lot. Alright, so now we are finished. We calculated the probability of getting Prince Charming for each test group size between 350 and 400. And now let's plot the results here. So here we have on the x-axis the size of the test group between 350 and 400. And we can see here that we have here the maximum probability. And the maximum is at the x-axis value of 364. And the maximum probability is on the y-axis 36.7%. And you still can see here the random noise. But this is no surprise because we actually have zoomed in here very heavily. So you can see here on the y-axis that we have values from 36.5% till 36.7%. And let's exit here the interactive mode. And we can also find the maximum probability by using the max function on our results list. And we round here the result to 3 digits. So let's do this. And we get here a maximum probability of 36.7%. And we can also determine on which position of our results list we can find here the maximum with the method argmax. So before we have to transform our list into a NumPy array, and a NumPy array has the method argmax. So let's do this. So now we can see that on the 14th position of our results list or results array, we can find the maximum of 36.7%. And as we are starting here from 350, so 350 plus 14 gives us 364. So now we can also calculate the optimal relative test group size by just adding here 350 plus 14 divided by 1000. So the optimal test group size is 36.4%. And now we can also print out our results here in a sentence. So let's do this. And we get here the optimal test group size is 36.4% of the total applicants in order to have the maximum probability of 36.7% to select the best candidate. And now comes the interesting part. So there also exists a quite simple mathematical solution for our problem, and this is called the 1 divided by e law of best choice. And E stands actually for the Euler number, which is a mathematical constant and which is the base of the natural logarithm. And E is approximately 2.7182. And what actually the 1 divided by E law says, that the optimal test group size is actually 1 divided by E times the total amount of applicants. So let's first of all calculate 1 divided by E and round it to 3 digits. And we assign it to the variable 1div e, so let's print this out also. And here we get that the optimal test group size is actually 36.8% of the total number of applicants. And sometimes here the law is also called the double 1 divided by e law, because we not only find the optimal test group size at 1 divided by e, but also the resulting maximum probability of finding the best choice is actually also 1 divided by e. And we can also print out here the result of our mathematical analysis, and here it says the mathematically optimal test group size is 36.8% of the total number of applicants in order to have the maximum probability of 36.8% to select the best candidate. And if we compare here the mathematically or theoretically optimal solution to our solution that we find with our Python simulation, so we are quite close here actually. So here with the optimal test group size we are 0.4 percentage points away, and with the maximum probability we are only 0.1 percentage points away from the mathematically correct solution. So our Python simulation did a great job, and I would think that if we increase the amount of simulations further, or we further scale up the amount of applicants, then we would get even closer here to 36.8%. Alright, now so we were able to actually optimize our strategy to maximize the probability to find Prince Charming. So the optimal test group size is actually 36.8% of the total applicants. And in the next video we want to maximize the average quality or the expected quality of our selected princes. So hope to see you there. Bye.